Throughout the history of mathematics, one of the most enduring challenges has been the calculation of the ratio between a circle's circumference and diameter, which has come to be known by the Greek letter pi. From ancient Babylonia to the Middle Ages in Europe to the present day of supercomputers, mathematicians have been striving to calculate this mysterious number. They have searched for exact fractions, formulas, and, more recently, patterns in the long string of numbers starting with 3.14, which is generally shortened to 3. William L. Schaff once said, "Probably no symbol in mathematics has evoked as much mystery, romanticism, misconception, and human interest as the number pi." We will probably never know who first discovered that the ratio between circle circumference and diameter is constant, nor will we ever know who first tried to calculate this ratio. The people who initiated the hunt for pi were the Babylonians and the Egyptians nearly 4,000 years ago. It is not clear how they found their approximation for pi, but one source makes the claim that they simply made a big circle, and then measured the circumference and diameter with a piece of rope. They used this method and found that pi was slightly greater than 3, and came up with the value 3/1/8, or 3.125. However, this theory is probably a fantasy based on misinterpretation of the Greek word harpadonopte, which Democritus once mentioned in a letter to a colleague. The word literally means rope stretchers or rope fasteners. The misconception is that these men were stretching ropes in order to calculate circles, when they were actually making measurements in order to mark the property limits and areas for temples. A famous Egyptian piece of papyrus gives us another ancient estimation for pi, dated around 1650 BC or so. The Rind Papyrus was written by a scribe named Ahmes. Ahmes wrote, "Cut off 1/9 of a diameter and construct a square upon the remainder. This has the same area as the circle." In other words, he implied that pi equals 3.16, which is fairly accurate, but not quite on the dot. Word of this did not spread to the east, however, as the Chinese used the inaccurate value pi equals 3 hundreds of years later. When the Greeks took up the problem, they took two revolutionary steps to find pi. Antiphon and Bryson of Heraclea came up with an innovative idea for inscribing a polygon inside of a circle, finding its area and doubling the sides over and over. Sooner or later, they figured, there would be so many sides that the polygon would be a circle. Later, Bryson also calculated the area of polygons circumscribing the circle. This was most likely the first time that a mathematical result was determined through the use of upper and lower bounds. Unfortunately, the work boiled down to finding the areas of hundreds of tiny triangles, which was very complicated. So their work only resulted in a few digits. At the same time, Anaxagoras of Clazomenae started working on a problem that would not be conclusively solved for over 2,000 years. After imprisonment for unlawful preaching, Anaxagoras passed his time attempting to square the circle. Koshori writes, "This is the first time in the history of mathematics that we would find the mention of the famous problem of the quadrature of the circle, the rock that upon which so many reputations have been destroyed." Anaxagoras did not offer any solution of it, and seems to have luckily escaped paralogisms. If anybody can figure out what that means, well, that would just be grand. Since the time, dozens of mathematicians would rack their brains trying to find a way to draw a square with an equal area to a given circle. Some would maintain that they had found methods to solve the problem, while others would argue that it was impossible. The problem was finally laid to rest in the 19th century. However, the first man to really make an impact on the calculation of pi was the Greek Archimedes of Syracuse. Where Antiphon and Bryson left off with their inscribed and circumscribed polygons, Archimedes took up the challenge. However, he used a slightly different method than they used. Archimedes focused on the polygon's perimeters as opposed to their areas, so that he approximated the circle's circumference instead of the area. He started with an inscribed and circumscribed hexagon, then doubled the sides 4 times to finish with 96-sided polygons. For the next few hundred years, no significant breakthroughs were made in the search of pi. Gradually, it passed from Europe to East. In the next several centuries, the earliest value of pi used in China was 3. In 263 AD, Liu Hui independently discovered the method used by Bryson and Antiphon, and calculated the perimeters of regular inscribed polygons from 12 all the way up to 192 sides, and arrived at the value pi equals 3.14159, which is absolutely correct as far as the first 5 digits go. Near the end of the 5th century, Su Chunqi and his son Su Kangqi came up with astonishing results when they calculated 3.1415926 is less than 3.145927. Therefore, pi must lie somewhere between those two numbers. The father and son duo used inscribed polygons with as many as 24,576 sides. Soon after, the Hindu mathematician Aryabhata gave the accurate value 62,832 over 20,000 equals 3.1416, as opposed to the Archimedes' inaccurate 2 over 7, which was frequently used, but he apparently never used it, nor did anyone else for several centuries, for that matter. Another Indian mathematician, Brahmagupta, took a novel approach. It calculated the perimeters of inscribed polygons with 12, 24, 48, and 96 sides. And then, armed with a bit of popularity as an approximation for pi for the last few hundred years, maybe because the square root of 10 is so easy to convey and to remember, this was a value that spread from India to Europe and was used by mathematicians throughout the Middle Ages. By the 9th century, mathematics and science proposed in the Arab cultures. It is unclear whether the Arabian mathematician Muhammad ibn Musa al-Khwarizmi attempted to calculate pi, but it is clear which values he used. He used the approximations 3 over 1 and 7 in the square root of 10 and 62,832 over 20,000. Strangely, though, the last and most accurate value was seemingly forgotten by the Arabs and replaced by less accurate values. After this, little progress was made until a pi explosion in the end of the 16th century. Oh my goodness, I don't even know how to say that. Some crazy named French lawyer and amateur but great mathematician used Archimedes' method, starting with 2 hexagons and doubling the number of sides 16 times, to finish with 393,216 sides. His final result was that 3.14159226355 over pi equals 3.14159265337. More importantly, though, other than those mumbo-jumbo numbers, Viete became the first man in history to describe pi using an infinite product. His formula was 2 over pi equals 1 over 2 over 1 over 2 plus 1 over 2 divided by 1 over 2 in the parentheses of 1 over 2 plus 1 over 2, 1 over 2 plus 1 over 2, 1 over 2 pi. Unfortunately, this equation is not too useful in calculating because it is just so gosh darn silly. It requires too many iterations before convergence, and the square roots become quite complicated. He did not even use his own formula in the calculation of pi. Still, it was an innovative discovery that would open up many doors in the future. In 1672, James Gregory wrote about a formula that can be used to calculate the angle given to tangent for angles up to 45 pi. The formula is arctan t equals t minus t3 over 3 plus t5 over 5 minus t7 over 7 plus t9 over 9. 10 years later, Gottfried Leibniz pointed out that since tan over 4 equals 1, the formula could be used to find pi. Thus, one of the most famous formulas for calculating pi was realized. 4 equals 1 minus 1 over 3 plus 1 over 5 minus 1 over 7 plus 1 over 9. This elegant and majestic formula is one of the simplest ever discovered to calculate pi. But it is still fairly useless. 300 terms of the series are required to get only 2 decimal places, and 10,000 terms are required for 4 decimal places. To compute 100 digits, you would have to calculate more terms than there are particles in the universe. However, this formula set the stage for a handful of other formulas that would be more effective. For example, using the knowledge that arctan 1 over 3 equals over 6, you can derive the following equation. 1 over 3 equals 6 equals 1 over 3 minus 1 over 3 over 3 over 3 again, plus 1 over 935. After some algebra, it simplifies to not that simple of a number. Using only 6 terms of this formula, one can calculate that pi equals 3.141309, which isn't too far from the real value. Surely, the 17th century mathematicians were onto something. It was just a matter of time until they discovered a formula that was even better. By 1750, the number pi had been expressed by an infinite series. Its value had been computed to over 100 digits. It had been given its present symbol. All these efforts, however, had not contributed to the solution of the ancient problem of the quadrature of the circle. The first step was taken by the Swiss mathematician Johann Heinrich Lambert, when he proved the irrationality of pi first in 1761, and then in more detail in 1767. His argument was, in its simplest form, that if x is a rational number, then tan x cannot be rational. Since tan pi over 4 equals 1, pi over 4 cannot possibly be rational, and therefore pi is irrational. Some people felt that his proof was not rigorous enough, but in 1794, Adrien Marie Legendre gave another proof that satisfied everyone. Furthermore, Legendre also gave the first proof that 2 is irrational. From this point on, computers and other machines have provided in the vast and, might I say, expansive use and discovery of the number pi. Pi will forever be a number that will be remembered as that thing that reminds us of a tasty baked treat. The end.